Hey biology class, it's Hugh here. We're back for the second part of my explanation of how neurons work and the end part of the course. This is in the homeostasis unit. And last time we looked at part one of the neuron and how it works. And you should watch that video, make sure you do before you go into this part. But just to summarize, so first of all, this is the end of one neuron. It's called the axon terminal. This is the beginning of the second neuron. It's called the dendrite. This gap in between is the very famous synapse. Just a tiny gap between two cell membranes. Okay. In preparation for the nervous signal to come, the engines of the neuron, the sodium-potassium pumps, are running all the time. They push out sodiums and they pull in potassiums. So 3 sodiums out, 2 potassiums in. And each one is working like that. The potassiums, once they come in, have the ability to leave through the potassium channel and they leak out. So that even establishes more positive charge outside the cell membrane. So the outside of the cell membrane is all positive. Because you've removed positives from a neutral solution, the inside of the membrane is negative. And this is called the resting potential, about negative 70 millivolts. So it's at that point that the neuron is ready to accept a signal. We have to start somewhere, so we start over here with a signal coming down and stimulating the vesicle here, which carries the neurotransmitter, little n. The one we'll talk about today is serotonin, probably the most famous one, but there's a bunch of different neurotransmitters. The stimulus reaches the end of the axon terminal and causes the vesicles to fuse with the presynaptic membrane, and it opens up and dumps the neurotransmitters into the synaptic cleft. So they're ready to cross. When they cross, they click in, because of shape recognition, to the receptors on these cells, and those are the ligand-gated sodium ion channels. So I'll just show you a couple here. When they click in, they open the channel and in pours the sodium. And remember, the sodium is positively charged. So then all these sodiums enter the dendrite. There's a couple there, there's more here. And they all enter the dendrite. And now, temporarily, this part of the neuron is positive inside and negative outside. The charges have been reversed. And that's the signal. So that's established the signal. If the signal is strong enough, it will activate, because of the fact that if you notice, remember the two types of green ones, these are the ligand-gated sodium ion channels, but these are voltage-gated sodium ion channels. So the presence of a change in voltage here activates nearby voltage-gated sodium channels, and these guys pop open. These guys, of course, down here don't recognize it. But when this pops open, then all of a sudden there's a positive charge here. And these guys propagate down the neuron, down the axon. In their wake, as they pass, these guys close up again. So the neurotransmitters don't stay in there all the time. They pop back out. When they pop back out, these guys close, and then the sodium-potassium pumps can take over and regenerate that negative potential inside. What in fact happens is that many of these neurotransmitters are pulled back. It's called a reuptake, so that the axon terminal of this neuron pulls them back in a process called receptor-mediated endocytosis, and pull back the neurotransmitters from the synaptic cleft. So they get removed. Okay. As we go on with the, process here, we just go along the neuron and then the axon, and it's the exact same process as we go along. The voltage-gated sodium channels are all the way along here. So the wave of depolarization, the wave of positive charge, propagates along until it hits the end of the axon terminal down here. And this is where we meet the final type of ion channel. These are the calcium-gated ion channels. Well, the calcium-gated ion channel, or they're voltage-gated calcium ion channels. The voltage change here causes them to pop open, And this is what stimulates the jump of the neurotransmitter. Calciums that come in here, Ca2 pluses, that come in through these calcium ion channels, bind to the vesicles and cause them to fuse and then to dump their neurotransmitter into the next synapse, and we're off again. And that is how a neuron works. So summarization is that there's a wave of positive charge that propagates down the neuron from the dendrite to the cell body to the axon terminal. And in the wake, as soon as it flows past a point, as soon as the positive charge flows past, then the sodium-potassium pump, which is always running, reestablishes the negative potential inside. This is how it all works, and you might think this is not efficient because, of course, this process here is a slow process. You've got to have a diffusion event from here to here, and even though it's a very short distance, it's much slower than the propagation of the voltage down the cell. But what's very important here is to realize that this synapse and combinations of synapses act like gates in a computer chip, and that's what allows cells to make decisions. And that's the really cool thing, is that depending on the situation. So although I've drawn one axon terminal and one dendrite, quite possible is that you have 5 or 6 different axon terminals all attached to the same dendrite. And then if one fires, it may not be enough to stimulate the pulse. You might need 2 or even 3 to fire, in which case this is like what we call in computer science an AND gate in logic circuitry. Unless you have this and unless the 2 neurons are sending a signal simultaneously, the signal does not go through. And this is the basis of the logic of the wetware of your mind. And of course, it's similar to computers, but absolutely not the same in no way. Far more complex, far more interesting, and as I should say, far more unknown. Last thing to say here is that there's a class of drugs called SSRIs, and they're called selective serotonin reuptake inhibitors. So SSRI. And these are a class of psychopharmaceuticals which are generally called antidepressants. And what happens is that for some people, just naturally, your reuptake ability for serotonin, the neurotransmitter, is not as efficient as other people. Well, actually, no, sorry. For some people who have problems, it's far too efficient. It pulls out almost all the neurotransmitter, in which case it takes more of a signal, a greater signal to cause the stimulation. The selective serotonin reuptake inhibitors, these leave some neurotransmitters in the cleft so that the next signal is more likely to go through. So the theory is that depression in part is caused by a lack of cell communication, and the SSRI, the selective serotonin reuptake inhibitor, is a drug which prevents all the serotonin from being reuptaked and therefore makes the next signal much easier to happen. So that's one bit of interesting, how the chemistry of medications, drugs, and so on work. It's all based on this kind of understanding of the neuron. I think that's the end of the course, guys. I'm pretty much going to wrap it up here. We're going to focus on culminating activities online, but I hope you enjoyed the course. I hope you watched the video and post questions. I'll be here at 11 to talk about details